Hello everyone. In this video, we will be discussing about the energy calculation of molecular hydrogen ion using variation theorem, and we will be calculating the bond energy as well as bond length of hydrogen ion. Now, why do we do that? First of all, we have a question: how does an electron orbiting around the nuclei in an hydrogen atom? What is the force that are binding the nuclei, hydrogen nuclei and the electron? To answer the question, Schrödinger used his famous equation H psi is equal to E psi, where the E represents the energy that is required to the electron to be get binded to the nuclei, and this is very precise result we are obtained using this equation. And now how do we calculate this energy? We presume that the electron moving along a path by a function called a wave function psi, and the wave function is measured in spherical coordinate and it is called as atomic orbital, and the psi was acted upon a operator called Hamiltonian operator. Predominantly the Hamiltonian operator comprising two components: number one, kinetic energy, and number two, the potential energy. And because the hydrogen atom is a very simple system having one nuclei and one electron, it is readily calculated and the results are very precise. However, we know that the hydrogen remains as hydrogen molecule than that of staying as a single nascent hydrogen. Therefore, we now use the Schrödinger wave equation to calculate the energy E, meaning what is the force that are responsible for holding the two electrons and two nuclei together. And by doing that, we can estimate the energy, the same amount of energy if given, then all the nuclei and the electron could be separated out. Now for hydrogen molecule, we have to set up the Hamiltonian operator. However, the Hamiltonian operator seems to be very tedious one that makes the calculation really impossible. Why? Because there are so much of kinetic parameters as well as there is so much of potential parameters to be get incorporated. Fine. And therefore, Schrödinger wave equation works well or easy for the applications on hydrogen atom, but coming for a hydrogen molecule is difficult. And therefore, we want to look into a system that must contain the hydrogen molecule but one electron if present. That would be simplify the complexity that is involved in the hydrogen molecule. That's why we have chosen the hydrogen ion, because in case of hydrogen ion we have two nuclei, that is we are talking about hydrogen molecule. However, there is only one electron and therefore it is a simpler term. So once again, how do we construct this Hamiltonian? These are the parameters, and thereby when it acts on the psi, we will be able to generate this energy, and this energy is very similar to that of the hydrogen atom. Therefore, the hydrogen and hydrogen molecules will share many common parameters, but there are certain differences. Like in case of hydrogen, it is psi is denoted as wave function and it is measured in spherical coordinate and it is represented as atomic orbital. But coming into the hydrogen ion, it is measured in elliptical orbit, because see, this is the nuclei HA and we have nuclei HB, and this electron orbiting both the nuclei in an ellipsoidal manner. Therefore, it is an elliptical coordinate, and this orbital is no longer represented as atomic orbital but a molecular orbital. So to calculate the energy, there are various models that are available. Among the most popular are perturbation theorem and variation theorem. In this episode, we will be discussing about the variation theorem. Before going in that, actually experimentally the hydrogen ions energy was calculated, that the energy that keeps this electron and the nuclei intact. that is measured as bond dissociation energy, which is 2.8 electron volt, and the bond and the distance between the two nuclei is around 1.06 Armstrong units. However, the success of this theory, variations theory and molecular orbital theory, depends on how the calculating E value closer to these values. That is what we will be unraveling in this episode. So, how do we do this? First of all, we do this by 4 important subworks, which means we do this by dividing into 4 different tasks. First task, because we are doing it in a variations principle where where this E script is the energy. This energy can be calculated by psi of H operator psi in all space theta, and in order to normalize it, we have the denominator psi square d tau. So that will helpful for us to normalize things. So in order to apply in that equation, so as to find the energy, the first task is to construct a Hamiltonian. After constructing the Hamiltonian, next task is to set up a suitable trial wave function, and then we have to apply in the variation theorem and go for the calculations. Once we go for the calculations, then we can analyze the results, which is the task 4. So this episode is now focuses on all these 4 tasks. Let's get into the first task. The first task is to create a Hamiltonian. So we have hydrogen atom, nuclei A and nuclei B. We know that the Hamiltonian predominantly contains 2 components. One is kinetic energy and the other is potential energy. So the kinetic energy is given by minus of h cross divided by 2 pi ma. In certain books, in place of h cross, it is given as h divided by 2 pi. So if you prefer here over h, if you prefer h over h cross square, it will be 8 pi square. Fine. Now in this episode, for all practical purpose, we'll stick to the h cross, reduced Planck's constant. Now h cross square by 2 pi ma, where capital Ma represents the mass of nuclei Ma. So this is the kinetic energy of the kinetic energy caused by the spinning of the nuclei into delta A square, meaning this nucleus is measured or spinning in a 3-dimensional space. That's why it is given in a Laplacian operator, that is delta, which means delta means dxy, dx, dy and dz. Fine. Now in addition to the nuclei 1, we do have another nuclei B whose kinetic energy is given as minus of h square by 2 pi mb, where mb is the mass of nuclei B. And these are not only the participants that are having kinetic energy, but also the electron. Even this electron also orbiting the nuclei in an elliptical manner. Therefore, whose kinetic energy is given by minus of h cross square divided by 2 pi m, small m. Small m indicates the mass of the electron, and delta E square. So this is the kinetic energy. Now going into the potential energy. So the potential energy is a result of interactions or energy exchanges between the components. For example, here the nuclei attracts the electron. Therefore, this attraction is represented as E square by 4 pi epsilon Ra, where Ra is the distance between the nuclei and the electron. Likewise, this electron is also attracted by the another nuclei B, whose attractive force is given by minus E square by 4 pi epsilon Rb. Why do we use minus? The term minus indicates that they are in attraction. The nuclei attracting the electron. So what happens? Because of this attraction, there is less in energy spending, meaning they are more stable. So more the minus means more the stable, meaning less is the energy they will be spending. That is what given as minus. However, in addition to the attraction, there is also repulsion. Which is being repelled by whom? this nuclei HA, hydrogen A nucleus, actually repels the hydrogen B nuclei because they are in the closer proximity of the distance of R. So when they are closer together, there is a more repulsion which eventually increases the energy, and that's why it is given in the plus symbol. So the plus symbol means the energy is increased, and it is given by E square by 4 pi epsilon R, where capital R represents the distance between the two nuclei. So now we are having the kinetic energy term as well as potential energy term, putting together everything in a single line. This is the Hamiltonian. Fine. So this whole Hamiltonian seems to be very big, very complex. So we need to make it smaller to simplify one. How do we do that? To do that, Oppenheimer made an approximation. That is, the nucleus is moving as well as electron is moving. However, the nucleus is around 1840 times much heavy than that of electron. Therefore, it will move little slower. In other words, in the viewpoint of electron, the nucleus is actually seems to be stationary or not moving significantly. Taking this into account, we now consider that the nuclei A did not move at all. So this kinetic energy term immediately vanish. That's the advantage of Born-Oppenheimer approximation. We can successfully remove one term out of 6 terms. See, this is term 1, term 2, term 3, 4, 5 and 6. We have removed term 1. Likewise, the same applies for the nuclei B. Because B is very heavy, it will not move as fast as to compare with the movement of electron, and therefore in the viewpoint of electron, the nucleus B is actually seems to be stationary. Therefore it doesn't have kinetic energy. So we remove the kinetic energy term of the B. Therefore we have now only 4 terms. That is kinetic energy of the electron and the potential energy altogether. And that is the energy, or that is the parameters that are involved in the Hamiltonian are given here. But still, this seems to be very complex in nature. Though we have reduced 2 terms, still it seems to be complex. So how to simplify further? For which we have an idea of converting all these units into units to atomic units. When we go into atomic units, then preferably most of the term will vanish. How does it vanish? For example, we assume that the electrons seems to be unity, meaning the mass of the electron is unity. As well as we assume that 4 pi epsilon whole value to be unity. Fine. Now, we now presume charge of the electron is 1, 4 pi epsilon is 1, even the h cross value is also 1, mass of the electron is also 1. Now, by doing this, what really happens is the h cross becomes 1, and this is simply 2 delta square, and this will be simply 1, 4 pi epsilon will be vanishing, so we will be having RA, and this will be 1 divided by RB, and this will be simply 1 divided by capital R. This is the very simplified Hamiltonian for the hydrogen ion. Okay. Now, so that is how we have come up for the Hamiltonian construction. Fine. So task 1 is over. Now let's quickly move on to the task 2. That is, we need to set up a trial wave. So what is a trial wave means? Trial wave means we have to fix a wave function for the electron. So let us presume there is only one electron, and that electron is somewhat closer to the nuclei, and this nuclei can be simply written as a trial wave function phi towards the nuclei 1. Nuclei A, we have a coefficient Ca, and the wave function psi is in 1s A. However, this electron is also tied to the nuclei B, whose coefficient is Cb. And what is the wave function of that electron with respect to nuclei? That is psi 1 sb. Now this is how we set up a trial wave function. So this is a trial wave function. As I told earlier, C represents the coefficient of nuclei A. Psi A 1sa represents the wave function of the electron with respect to A nuclei, and psi B 1sb with respect to that of the nuclei B. So task 2 is also completed. Now we'll go for the task 3. Task 3 is the very biggest task. That is, we need to fit the values trial wave function in the variation theorem. This is the variation theorem. If you want to calculate the energy E script, then you have to put the trial wave function that is also operating on Hamiltonian in all given space. If it is not normalized, we need to normalize by the denominator. Now in the place of phi, we put our value trial wave function, that is Ca psi 1a plus Cb psi 1b, and H operating on Ca psi 1sa Cb psi b 1sb. This is our numerator, followed by for normalizing purpose we have the denominator. To make it very simple, first we will be solving for numerator. That is the first we do it, followed by the denominator, and after having denominator and numerator separately, we'll divide each other to get the energy. That's the idea. Now moving on to the numerator. For the numerator, we assume that the two trial wave function where the second one is being operated by the Hamiltonian. Fine. So we have to put the Hamiltonian over here. How do we put the Hamiltonian here? Minus of 1 by 2 delta square minus of 1 divided by Ra minus of 1 divided by Rb plus 1 divided by capital R. By applying all these things, we can solve it, but as a sort of a mnemonic, we can have that. This as our mnemonic. Fine. So first of all, we separate and do it. This is the very first term. This first term is multiplied with the other term. Fine. Ca, C are constant, so they are non-square integratable, so we take it as Ca square, and integration of psi A 1sa of H cross psi A 1sa. So we having the first term. Likewise, we'll go for the second term. That is this one multiplying with the other one. So once again Ca and Cb is constant, so taken out Ca Cb psi 1sa H cross operating on psi 1sb, so psi 1sb. Now second term is over. Now going for the third term. For the third term, what happens is this one acting on psi a. So Cb Ca taken out because they are constant, and psi b 1sb Hamiltonian followed by psi a 1sa, and finally this one. So we have this expansion. Now we have a sort of a simple identity thing such that psi a 1 sha integration of psi a 1 shk can be simply written as HAA. Therefore this is now turned into HAA. Likewise, this d tau psi a 1 sa hb can be represented as HAB. So we have HAB. Likewise, by taking into this identity, we are getting the numerator as CA square HAA, CACB HAB, CBCA HBA, and CB square HBB. You can cross refer it for your future use. This is taken from the book called Prasad, Quantum Chemistry. Now, numerator is finished. Now we'll move on to the denominator part. Denominator is actually very simple. This is our denominator, integration of Ca psi 1sa plus Cb psi 1sb into Ca psi sa plus Cb psi sb. So again we take this term multiplying this one directly, Ca square psi a square and 1sa square. First term is over. Now we'll go for the second term. That is, this one is multiplying with that one. So CA, CB, CA, CB, Psi A 1 as A and Psi B 1 as B. Second term over, and likewise we are doing for the third term as well as fourth term. We are having this one, and once again, now by cross referring this one, Psi A square can be simply, we know that we have calculated the denominator and earlier we have solved for numerator. Now all the both the value numerator and denominator applying in the variation theorem, we get this result. So what's next? The next thing is we have to solve so as to get this E script value. To solve it, this denominator to be multiplied to the left. That's what we'll be doing in the next step. So we will get this term. The denominator, initially it was in the denominator side, now it is brought to the left. So we have this equation. Now we rearrange. How do we rearrange? This RHS term brought to the LHS side. Therefore it becomes minus. So the overall equation now becomes 0. Now this equation is differentiated. That is, we differentiate the E script for coefficient A separately, and then one more time this equation will be differentiated for the E script, this time for coefficient B. So the same equation differentiated 2 times separately for 2 different coefficient will help to solve the this equation. So first, as I said earlier, we differentiate the whole equation for the CAA. Fine, CA. So this is the term. First we keep the CA square, CB square, 2CB CAS as a constant. So it simply becomes dou E. Fine, so this constant appears as if. Now second time we keep the E script constant and differentiating this one so that it will become 2CA. CB square will become obviously 0 for a reason, it's a constant, and 2CB yes is the next one. For this one it will be 2CA HAA and it will be 2CB HBA, and this whole term will become 0 because being constant. Fine. So this is what we are obtaining. Now we know that dou E with respect to dou CA is 0. Therefore this dou E will actually vanish from the term. Fine. So as a result we will get 2CA 2CBS equal to 2CA HB. So this is how we are getting equation. The next step, fourth equation. Now we divide them by 2 so that all the 2 will be simply get eliminated. So we are having this equation. Now we rearrange this equation. How do we rearrange this equation? We rearrange this equation by simply taking the LHS to the RHS side and making it 0. That is how CAHAA, CBHBB, it becomes minus of ECA, CBS and 0, because I multiplied. E script is multiplied to CA and E script is multiplied to CBS. Fine. Now we separate the variables. How do we separate the variables? This CAHAA and ECA are separated. So CA separated, HAA minus of E script. Fine. Likewise we separate the CB. How do we separate the CB? So CB is pulled out. Fine, CB is pulled out, and HAB minus of E script of S. E script of S. Now we have separated the coefficient CA and CB, and we are having a circular equation. Now this time we divide the whole of this equation with respect to CB. Fine. We know that this always will become 0, so we neglect it. This will become 2CB CAS and CAB, and dividing it all the 2 will be get eliminated. So we are having this equation, and one more time we rearranging such that this goes to the right side to become 0, and upon separating CA, okay, we separate CA, this CA and this CA as removed. Okay, so HAB minus of E script of S obtained, and likewise we separate for CB. When CB is pulled out, HAB minus of E script. Fine. So we are now having two separate secular equation 1 and 2. This can be turned into a matrix. Okay, so this matrix, if put set for 0, then it will become a secular determinant. We know that this will be multiplied, so it will be HAA minus of E into HBB minus of E script. We know that HAA and HBB are one and the same. Therefore it can be simply written as HA square. Fine. So that's the way to minimize the lots of parameter, in other words, to make it simplify. So this will be multiplied to this one, becomes HAE square. Likewise, this is multiplied with the other term, because we know that HAB is equal to HBA. Therefore, we will be readily solve these two equations. Now taking roots on both the side, the HAA minus yield will give 2 roots plus HABE minus and minus HABES. Now solving for the E and rearranging, we will get this equation. What are these? These are the two important results. Now by taking the Coulomb integral and other integral, we can plot separately for the two values in the graph. So these are the two graphs. Green line represents E plus and red line represents E minus. We can call it as Jared, and this is unjared, which means it is having lesser energy, lower limit, and this is the upper limit. So we are having two important results. Now these two important results are the one talks about the two orbitals, molecular orbitals. This is having lower energy level, this is having higher energy level. Electron in the lower energy level is highly stabilized because of least energy. However, electron in the excited level or in the higher energy level makes the electron to go unstable. Fine. And this will cause a constructive interference, therefore bonding happens. The electrons here will make a destructive interference, and therefore a nodal arises which makes the unstable. This is how we have constructed a molecular orbital by linearly combining the atomic orbitals. Fine. And we are getting the bond length of 1.32, which is very close to that of a real 1.06. Of course, our E value is little higher than that of 1.06 as expected by the variations model. However, it gives a fairly decent result. So thank you very much for the class.